So, there's this concept in programming that's incredibly powerful, but also, let's be honest, famously tricky. It's called recursion. And look, if it's ever felt like a total brain bender, trust me, you are not alone. But today, we're going to unravel it, and we're going to do it with a surprisingly simple tool. So, what in the world do these traditional Russian nesting dolls have to do with coding, right? It seems like a stretch. But it turns out they hold the visual secret to understanding recursion in a way that just clicks. And by the end of this, you're going to see that connection perfectly. All right, let's dive right in. What is recursion really? We're going to see how it's not just a technique, but a true problem-solving superpower, all seen through the lens of these nesting dolls. Okay, so at its very core, recursion is when a function calls itself to get a job done. I mean, think about that for a sec. A process that literally contains a smaller copy of the exact same process. It's the perfect analogy for opening up a nesting doll, only to find another, slightly smaller, identical doll waiting inside. You're just repeating the same action, opening on a smaller version of the original. And this right here is the key takeaway. It's so important. You keep repeating the action, you keep going deeper and deeper, but eventually you have to stop. With the dolls, it's that final, tiny, solid one that just doesn't open. In our code, having this final step is non-negotiable. It's everything. Okay, so how do we actually think this way? How do you build one of these recursive functions? Well, it turns out that every single one, no matter how wild or complicated, is built on two simple golden rules. And here they are. First up, you've got the base case. Think of this as your safety net, your stop sign. It's the simplest possible version of the problem, the one that doesn't need to call itself again. It's that smallest doll. Then you've got the recursive step. This is the action itself. It's you opening the doll. It's the part of the code that says, okay, I'm going to call myself again, but on a problem that's one step closer to that base case. And let me tell you, you cannot forget that base case. Because without it, without that stopping point, the function would just call itself again and again and again forever, like a set of nesting dolls that just never ends. In the coding world, this triggers something called a stack overflow, and poof, your program crashes. Okay, theory is one thing, but let's get our hands dirty, right? Let's see these two rules in action. We're going to tackle a classic problem that's just a perfect fit for this kind of thinking, calculating a factorial. So first things first, what's a factorial? It's written with an exclamation mark, and it's simply the product of all the whole numbers from that number all the way down to 1. So 3 factorial is just 3 times 2 times 1. 5 factorial would be 5 times 4 times 3 times 2 times 1. Easy peasy. So let's follow the journey down the rabbit hole, or down the nesting dolls. To solve for the factorial of 3, our function can't do it yet. It says, hey, I need the answer from factorial of 2 first. And factorial of 2 says, well, I need the answer from factorial of 1. This keeps going one doll deeper each time until we hit factorial of 0. And that is our base case, the smallest doll in the set. The function knows this answer instantly by definition. The factorial of 0 is 1. And now for the magic. This is the journey back up. The base case, factorial of 0, hands its answer, which is 1, back to factorial of 1. Now factorial of 1 has what it needs. It calculates 1 times 1 and passes that result back up. Now factorial of 2 gets the answer it was waiting for. It calculates 2 times 1 and passes that result, 2, back up. Finally, our original call, factorial of 3, gets the answer it needed all along, and it can finish its job, 3 times 2. And there it is, our final answer, 6. See how elegant that is? It's beautiful, right? Instead of some big, messy calculation, we just broke the problem down into this clean chain of smaller, identical problems until we hit one we could solve. And then we just built the answer back up. So you might be thinking, okay, that's a cool little coding puzzle, but where would I ever really use this? Well, it turns out this way of thinking is hiding in plain sight, all over the place. Well, think about searching for a file on your computer. The search function looks in a folder. No file? Okay. Now it runs the exact same search on every single subfolder. See? That's recursion in action. Or think about a family tree. To find all your ancestors, you find your parents,
And then you run the exact same find the parents process on them. It's a naturally recursive idea.
And that's the whole point, really. Recursive thinking is this master key for any problem that can be defined in terms of a smaller version of itself. It's about learning to see the solution to a huge, complex task by finding the solution to its simplest part.
So the next time you're facing a really tangled up problem, whether it's in your code or just something in life, try to take a step back and think like a nesting doll. Ask yourself, what's the absolute simplest version of this problem I can solve? And how can I use that simple solution to solve the next biggest one?
All right, so I'll leave you with a little challenge to chew on to really test out your new superpower. How would you use recursion to reverse a string of text, like the word hello? Think about it. What's the base case? The simplest string to reverse. And what's the recursive step? Give it a shot. It's the perfect way to make this powerful concept truly your own.